All right, how's it going, everybody? Welcome here to the first day of week 5. Um, we left off last week. We covered section 7.1. We're back in chapter 7, getting some more integration techniques. The cool thing about today is that you're not going to see a new integration technique at all. We're just going to stop and remember that the things that you learned in trig weren't easy, and we want to be able to see that those things are going to apply to calculus scenarios here as well. And so today, in a sense, is not really getting us new calculus. It's just letting us see how the things that we learned in trig are going to help us with our calculus here. So in a sense, this isn't new trig and this isn't new calculus. This is just us seeing how the things we learned in trig help us do calculus here today. Um, so this section is all about using your trig knowledge to rewrite integrands, the expressions inside of integrals, to make them integrable, possible to integrate. My general statement here is that every single one of you should have easy access to a trig identity sheet for the rest of your lives. That is something you will always want to be able to look stuff up on rather than plan to memorize everything all the time. Memorization is usually not worth our time, and the further and further you go in school, the more and more it matters that you are good at using your resources rather than trying to memorize everything that you come across. So the trig textbook that is typically used at CR, I think that a lot of, if you guys took trig through College of the Redwoods, then I'm pretty sure that you used, actually, do I have it sitting right here? My Purple Sullivan textbook right here. Um, this guy, it didn't even occur to me that I actually had it sitting right here, but this is the book that we've used at College of the Redwoods. And it really doesn't matter. What you need is a trig book that has the really nice page of identities that we all know are in like the front and back cover of lots of math books like this. So I have a PDF of this because I'm laughing. I didn't even realize I had that book sitting on my desk here till just now. But I did post in Canvas. If you look in our module in Canvas, you'll see that I did post the PDF of this right here. And so what I'm talking about is this guy right here. Here's all of our trig identities that we learned in trig. Basically, trig class is like learn where all this stuff comes from, right? And the way that trig class goes is that the first couple weeks of trig class, we define like our basic trig like definitions up top here. I don't expect anybody really needs any of this stuff. This is just saying like, hey, do you remember how sine and cosine are defined relative to a triangle and relative to each other? Trigonometric identities, this is the stuff right here where I expect all of you to have seen all of this at least once. I expect none of you to have even half of this memorized right here. What I do expect is that you could see something that looks like one of these identities and say to yourself, oh man, I feel like that's like some trig identity I'm supposed to know, and then go look it up. All you need is, in a sense, the vaguest familiarity with the things that are going on in this formula sheet right here. And that's good enough. As long as you can look at something and say, I feel like there's an identity that's related to that that might allow us to rewrite something, that's all you need. Then you go and look it up. So this trig identity sheet, this is sort of one of those things where it's like, I mean, you should like have this out when we go to take our first test, because otherwise there's going to be stuff on there that you're not going to know how to manipulate, right? So a lot of what today is manipulating our integrands to go from things that aren't integrable to rewrite them so that they are integrable. And we will reference back to this trig identity sheet here several times today because we're going to need some of these things. And again, I do exactly what I just said. When I see things that have like a sine squared in it, I'm like, all right, I know there's a couple different ways that I could rewrite sine squared. And I'm looking at a couple of them on my sheet right here. I see a sine squared hanging out right here. So it looks like sine squared could get turned into like a 1 minus cosine squared. I also see a sine squared right here. It looks like sine squared could actually be cosine squared minus cosine 2 theta, right? Stuff like that. Or sine squared could be rewritten using this double angle formula right here. So again, it's not that you need to memorize what they are, but you need to know to yourself, ooh, that's a trig expression that could be rewritten to look like something else. Let's go look it up and see what our options are here. So referencing this table, pretty dang important. If you want to grab the one that I've got here, you can go over to Canvas and it should just be sitting in our week 5 module just as a PDF sitting right there and you can download it. So we'll certainly reference this quite a bit today, and you should for the homework and stuff like that as well. So how are we going to do this stuff? Well, In general, if I'm thinking back to trig class, my technique in a lot of things that I do in trig is to say, well, there's actually really only two trig functions that there are out there. So in trig, I like to just convert everything to sines and cosines and say, okay, now let's actually manipulate this thing. We're going to find that that's not really a good technique for us in calculus land here, but stuff like that is a good idea where we can kind of set up these like general rules to say, okay, first think about these parts here and then see if you can mash it all together. So when we're performing trig integration, we want a different technique than the one that I just described. Going into sine and cosine for everything is not necessarily going to be our best move. Instead, what we want to think about is the fact that in both u sub and integration by parts, what we're looking to do is identify two components of our integrand. One, some part, two, the derivative of that part. That's kind of how we keep on identifying u sub and integration by parts, is recognizing that we have both a component and the derivative of a component, and we want to identify those as like our u or our u and our v, stuff like that. So what we kind of want to remember here is that rather than thinking that like sines and cosines play nice together, we want to be thinking to ourselves things like an object and its derivative play nice together. Right? That's kind of the related parts that we've got right here. So that being the case, it kind of matters that we remember what our trig derivatives are. I would like to point out to you that I absolutely expect that any of you should be able to come up with any of these at any time. And the reason is because out of all these here, the only one that I have memorized is the very first one. All the rest of them, I just know why it's true. I know that the derivative of sine is cosine. By the way, all these are going to get a plus c. I'm not going to write it. I'm just going to write plus c at the top right there. The derivative of sine is cosine. Therefore, okay, I guess I sort of have these first two memorized right here. The derivative of cosine is going to be negative sine. Our derivative of tangent, we think of tangent as being the derivative of sine over cosine, and that's going to lead us to a quotient rule. We're going to get low d high, so that's cosine times cosine for a cosine squared, minus high d low minus sine times the derivative of cosine. So it's really minus sine times negative sine, which really makes that plus sine squared of x, all divided by low squared. So that's cosine squared of x. And so I knew I was going to give myself a little bit more room right here. So for this guy here, it looks like what we're seeing for our derivative of tangent is, and we're remembering our trig identities right now, we've got 1 on top, we've got cosine squared on bottom, and that is secant squared. So we'll see one of these come up here today, that the derivative of tangent is secant squared. We can do cotangent similarly, but I just want to encourage you to think that I can, in a sense, do this in my head. The top part of my quotient rule should essentially be the same, but we're going to have the two parts flipped because the role of sine and cosine are now in different locations. What that really means to me here is that we're going to get the same values here, but because they're in flipped order, we're actually going to get the negatives of them, because where sine is going to be cosine, and where cosine is, we're going to get sine. And so here we're going to end up with a -1 on top. Similarly, we're going to end up, instead of a cosine on bottom, we now have sine on bottom. So there should be a sine squared down here. And so that's really the same thing as negative cosecant of x. All right, so that's our derivative there for cotangent, is the negative cosecant squared. Sorry, cosecant squared of x. We can do some more quotient rule for secant and cosecant. Our derivative of secant is the derivative of 1 over cosine. And here, low d high is 0, since the derivative of 1 is 0, minus high d low. The derivative of cosine is negative sine, so that's just a sine right there, all divided by low squared. That's cosine of x. So, oops, that's cosine of x squared. So this is typically written as sine over one of the cosines is tangent, and then 1 over the other cosine is secant. So tangent secant is the derivative of secant. And we get a very similar thing over here for cosecant. This is the derivative of 1 over sine. Low d high is 0 again, minus high d low is just cosine, all over low squared, which is sine squared of x. Uh, Reed, if you oh, did it there? We got a. Okay, I can agree that I did just see a thing drop down to saying 0, and now it has numbers over there again. Is it back there? A little more spotty here today. I did see that I agree with your statement of it to kind of, yeah. It, I agree that I think it might have been out, and I think that it might be hopefully back right now. So, yeah, refresh is kind of unfortunately always the good move right there. So. And so wrapping this guy up over here, notice negative cosine over one of the sines is negative cotangent, and then 1 over sine is cosecant. Yeah, cool. Glad you guys are on it. Hey, look at all those people we got in chat all at once right here. Good for you guys. So just remember with these derivatives, this is one of those things where like, I probably expect you, let me just draw this on here right now. I think that it's reasonable for me to expect that you certainly have these ones memorized. And I'm going to say that because those are the ones that I have memorized. I think that the other three are the ones that are a little bit weirder, although remembering this one is pretty easy when I remember this one. It's just sort of the opposite in both ways. This was positive, so this is negative because the order of subtraction flipped. This one had cosines on bottom, this one had sines on bottom, so secant to cosecant right there. These ones are a bit weirder. I often have to double check these ones and look them up and stuff like that, and that's okay. Remember that I've kind of said this a bunch of times this semester, like we're now at the point where memorizing things is not what your goal is. It's using your resources. And so um, don't let these things be roadblocks. If you need to look up a derivative, look up a derivative. You should be able to come up with these doing a little bit of quotient rule on your own, but you should also be able to just look them up right here. So in any event, we're expecting to see things like not just the 6 traditional trig functions, but if I see like a secant squared, that's going to be screaming to me, man, I hope there's tangent involved somehow, because I want to see an object and its derivative in an integrand so I can do something like a u sub or an integration by parts, right? We'll see one good example with some of these guys cropping up here today as well. So let's start looking at some examples here. As usual, I'm trying to pick some examples, like obviously not just do the book examples here. I will do 2 book examples here, but I'm picking those out for special reasons. So we'll get some other ones that aren't worked out directly in the examples in the book. So I like doing this one just because this kind of gives us the flavor of what we're doing, but this is like the easiest one that we could ever possibly see. It's not directly obvious though, just because it's the easiest of the non-obvious trig integrals. It doesn't mean it's really obvious, but we have already done this one before. So the thing I like to say is that when you get into calculus, it's no longer your best idea to convert everything to sines and cosines, with the exception of this one right here. This is like the one time where like I don't know what else I'd do. And so in this guy here, and again, we already did this one when we talked u sub here. But in this case here, it is pretty helpful for us to rewrite this in terms of sine and cosine. And the reason why it's helpful, though, is not because sines and cosines are generally nice to work with. It's because cosine is the derivative of sine. Like, that's the thing that makes this nice for us here. I think the thing that we did the last time we saw this problem is that we saw that the u sub here almost works both ways, but not quite, because this dx is certainly a member of the numerator up here. So what I'm thinking to myself here is I could start trying to make my choice here of u equals sine x, but then I would get du equals cos x dx, and that part right there is not right, right? We don't have a cos x dx because the dx is in the numerator, not in the denominator there. So those two parts are split vertically, but in our du term, they're combined, and that's just not what we have right here. So it doesn't look like this is what we actually want to do here. Instead, then I'll make my other u sub choice. I'm going to let u be cosine instead, and let du then should be negative sine x dx. And this does work out because I do have a sine x dx as one collective term up here in the numerator. So it looks like I can rewrite this as, notice we're picking up a little negative right there, that's extra, negative integral of sine x dx just becomes du, and 1 over cosine is 1 over u. This is a nice easy integral now. Now we get negative natural log of the absolute value of u plus c, and that's going to give us negative natural log of cosine. Now, The book writes this one actually slightly differently, and that's because we can think of this negative right here as a negative 1 power, and we know that the log property associated with multiple constant coefficients is that this could be represented as the power that's on the inside right there, right? So a negative 1 power on cosine turns that into a secant. So this could also be rewritten as the natural log of secant of x plus c, right? That negative as a coefficient could be thought of as a negative 1 power, so a 1 over cosine of x, and 1 over cosine is secant. So either of these are acceptable ways for us to write our answer. I don't necessarily know that one of those is better than the other. In fact, I should honestly say, I actually kind of think the cosine version is easier right here. I think the book just liked to subtract, deal with that negative, but I don't know. These are approximately equivalent to me. I don't see any real distinction here between these two. So in any event, here's our good thoughts right here to kind of get us going for the day. When we see these trig integrals here, we want to be hunting for appropriate pairings of an item and its derivative, and it matters that we get the parts in the right locations. Just because here we had a sine, a cosine, and a dx, they weren't combined in the right orderings, right? The cosine is in the denominator, dx is in the numerator. They're separated, but here our du term had them together. So that wasn't quite the correct substitution that we wanted to make right there. So we fixed it by making the other choice right here. As it's gone for you guys in 7-1, it's going to be the case that you're going to make some wrong guesses for U sub and for integration by parts, and that's okay. We can always just try another choice here, and we'll see some of that crop up here today. So there's kind of our first easy one right there. And again, I want to put easy in quotes because it's not super duper obvious that that's what's happening, right? We had to make a manipulation of the integrand to then allow us to use one of our integration techniques right there. So a lot of what today is about is it's not doing new calculus, it's remembering that we know how to manipulate trig expressions only trigonometrically. Then that's going to help us to be able to perform the calculus that we want to be able to perform. So let's go ahead and look at one that's a little bit gnarlier than that one right there. Something that's got a little bit more excitement to it here. Can I make this bigger here? There we go. Okay. So sine to the 6th of x times cosine cubed of x. And so what I'm going to do today is I'm going to intentionally set up some not correct u subs in integration by parts, just so that we can see which ones are right and which one's wrong. A lot of this is, in a sense, trial and error stuff, right? So here's the thing I'm thinking. My first thought that I might go into this right away with, if I'm a pretty good calculus student, but that's kind of not seeing all the things quite yet, is the thing that makes me happy here is I have a sine and I have a cosine dx. That leads me to believe that I can kind of just make the substitution we started with last time, right? So I'm going to make my first attempt at laying this guy out as, let's just pick u to be sine of x, and let's pick du to be cosine of x dx. So is this going to get me there or not? That's the question that I'm asking. So the thing that's kind of good here is that this sine to the 6th of x, that's certainly just u to the 6th as we've got it written right now. But here's my problem. This is not quite what we've got here, right? I guess I could write this as, I can see that I have a cosine squared of x times cos x dx, and this is du. That's certainly true. But what am I going to do with this little guy right here? It's not really quite clear to me what's going to happen there. So my question then to you would be, well, is there any way that you can use the fact that u is sine of x to make a statement about what cosine squared is? And hopefully you guys remember the maybe single most important of all of our trig identities. I'm going to pop over to look at it now. I think the most important single one trig identity out of all of them to remember, if you had to literally only memorize one thing, okay, all right. Technically, these are considered, in a sense, identity. This is just the definition of the function. Of the identities that are down here, I just got to think that this Pythagorean identity, oh wait, can I not? Oh, I can't write on this thing right here. That's okay. The Pythagorean identity, sine squared plus cosine squared equals 1, it's got to be our most practical thing that we're ever going to use right here. It's helping us convert between sines and cosines as long as we have squared terms that we're looking at right here. These collectively are referred to as the Pythagorean identities, all three of these right here. All three of these are just rewordings of the same thing. You should notice that if you take the original one, the sine squared plus cosine squared equals 1, you can divide both sides by sine squared, and you will get the second expression. Or you could take the original and divide both sides by cosine squared. No, I said that backwards. If you divide by cosine squared, you get the second one. And if you divide by sine squared, you get the third one. So these are all just rewritten versions of each other. So these Pythagorean identities, super duper helpful here for us. And so what I'm kind of thinking to myself is, let's go ahead and kind of rephrase this problem in a maybe slightly smarter way right now, right? So I'm going to kind of rewrite this problem for myself. So here's what I'm thinking. What I know is that my du term is going to end up looking like just one single cosine to be partnered up with a dx. So I'm thinking to myself, I'm going to do that for myself right off the bat. I'm going to separate these guys just like I sort of suggested I could have a moment ago. The reason I think this is smart is because I'm leading myself to set myself up for a u sub where I can select sine to be u. That's going to give me my cosine x dx. And I think the only smart thing I've got to do now is use my Pythagorean identity here to also rewrite this in terms of some sine stuff. So you should notice that actually what I was setting up before was gonna work out fine for me. I just felt like I like to do my trig beforehand rather than trying to start doing a substitution, then screw around with the trig stuff. That just feels a little out of order to me, so I generally try to avoid doing that. You should notice that the way that I've broken this down now is I've ripped apart the cosine cubed. I think the important thing that we want to recognize here is that we really like even powers on trig functions because it really helps us rewrite them in terms of a different trig function by using the identities that we have. Those are always associated with those even powers out there. There is no like identity for sine cubed, right? The identity is about the even powers of sine. So if we have an odd grouping like cosine cubed, it's very typically a good strategy in a lot of these cases to separate out the odd one and then leave the even pairings evenly paired together like I did right there. That means that the even pairings can be rewritten as their other trig term, which might be more palatable for us for our u sub. So now as I go to actually set up my u sub for myself, I think I'm actually going to be able to make something nice happen here. Now if I let u just be sine of x, then du can be cos x dx. And I've got all these parts in here. It looks like this is really just now u to the sixth, 1 minus u squared, and this stuff, cos x dx, that's just du. So I didn't know what the heck to do with this at first. I certainly don't have an antiderivative for the original. But when we did a little bit of manipulation to set ourselves up for a u sub, this actually turns into a very easy polynomial integral right now. So it looks like I can just do integral here. Let's do this. I'm going to say equals. I'm going to multiply this out. I'm going to try and keep this all on one page here. This is going to give me a 1/7 u to the 7th minus 1/9 u to the 9th plus c. And we can then rewrite that back in terms of our original variable. 1/7 times sine to the 7th of x minus stop pressing control thing, minus 1/9 sine to the 9th of x plus c. Right. All right, so this is our first like semi-easy one, and none of these are really easy, but all of these are ones where somebody else suggests to you the first little, I refer to these as algebra steps, but officially these are like trig steps, right? But the whole point here is the trig manipulation is what made this doable. And then we just land back at a easy integration scenario again, or easy integration if you're down with your u sub and your integration by parts. So a lot of what the 7.2 section is about is just saying, do some calculus, or sorry, do some trig first. When you're done doing trig, then go do the calculus you already know how to do. So there's not really new calculus to be doing here today. There's really just do the trig first. This is saying make sure you manipulate things cleverly first to set yourself up for your U sub. You should notice that I did some smart stuff up here and that I could have just kept going from here right away. I could have just rewritten that as my 1 minus sine squared. It's totally okay to have mixed u's and x's as you're like feeling your way through these problems right here. But notice again that kind of my strategy here was sort of like guess and check. I just flopped out there a U sub that I was just hopeful would work because it was easy for me. I saw that it mostly got my parts. It handled my sine stuff well. It handled part of my cosine stuff well. It handled my dx stuff. I just had some little bit of extra parts. The extra parts of cosine squared x, I stopped and I said to myself, is there any way for me to write cosine squared of x in terms of u, given that u is sine x? And that led me to think to myself, you know what? I do know things about how to rewrite squared trig expressions in terms of other squared trig expressions. And cosine and sine have that relationship. So it allowed us to do that little bit of rewriting right there. So my lesson that I think that we should be taking away from number 2 right here is it's okay to do, in a sense, like some guess and check. Just try a U sub and see how close you are. See what parts you can't get to agree with or can't get, in a sense, converted into your new variable, and then stop and say, okay, what trig can I do so that I can use my current defined expressions to get into our variable of interest right there? And we identified are pretty good. Maybe I should, if I'm keeping some slightly more responsible notes here. I'm clicking save. I should be clicking draw. Give me my draw. I think that our kind of the magic that happened in this one right here was really that we made our ever important substitution right there. That's our trig identity that we used right there. That was really important for the rewriting there. Got everything in terms that we wanted. So there's kind of our first example right here. This says homework problem number 2 out of the book right there, if you're curious where this came from. So let's go ahead and look at some more examples that sort of look like this, but sort of don't look like this, that are maybe a little bit tougher. So, and I just wrote here lesson to remind myself to talk about this. So again, I think what I want to say here that our lesson is with this one is even powers on trig functions means that you can use the Pythagorean identity. So anytime you see an odd power on a trig function being multiplied by other trig functions, it is often good strategy to extract one of them, the odd term, out to leave a bunch of even pairs with the other parts so that you can use your even pairs in your Pythagorean identity swap. I think that's our lesson here is look for those even and odd powers and help that influence your decision. When you read the section, you should see that the book does a super good job of giving you like a strategy box for when you see stuff of this format right here. And they specifically say, okay, yeah, it looks like based on the examples we saw, we should consider even and odd powers should help influence like the U sub choice that we make and the trig substitutions that we make right here. So think about picking off one of your powers to help leave yourself with even groupings. So we claim to like even groupings so much. How much do we like even groupings? Well, we like even groupings a lot, to the point where I want to kind of always think about things being in even groups. It helps me here. So the good thing about this integral right here is that we are looking at cosine to the 6th of theta d theta. And gosh, let me just do this since typing this and writing this is always a little bit more of a hassle for me. The book says theta. I typed it out as theta, and then I've decided it's just making things hard for me. Let me make this big here again as well. Nothing wrong with making a variable letter swap. We're going to do plenty of substitutions along the way. So this guy here. So initial thoughts. My first initial thought here is, I don't know an antiderivative for cosine to the 6th. That's my first thought. I'm always hoping that I can just straight up plop out an answer for this integral. Clearly can't do that here. The second thing I'm thinking is, well, if I'm going to use like a U sub or something like that, then I need to have both a part and its derivative in here. And I don't see that because currently I only have individual parts. The third thing that I'm thinking to myself is, well, at least I have an even power on the 6th, because I know that lots of our trig stuff has to do with having a squared quantity of something in order to make it a substitution. So I'm going to go so far as to say, I don't quite know. Maybe we should pop over to our picture right here and see what we see. So we're hunting for some way to rewrite cosine to the 6th in a way that's going to be helpful for us. When I see cosine to the 6th, I'm thinking to myself, that's three groups of cosine squared. And I think that because cosine squared pops up a bunch of places, right? We see cosine squared here. I see a cosine squared right here. I see a cosine squared right here. Right? There's a couple different places where I see a cosine squared that we could maybe do some manipulation. Now, one that I see that's of particular interest to me is this guy that's sitting right there. And the question is, why do I see this one as being more interesting than the others? And let's kind of talk our way through this process of elimination. If we're looking at this Pythagorean identity over here, what this says to me is I could swap out cosine to the sixth stuff, probably somehow, for sine to the sixth stuff. Not directly. It's not true that sine to the sixth plus cosine to the sixth is 1. But I think I could probably rewrite this in terms of, rewrite the cosine to the sixth as cosine squared cubed, then rewrite cosine squared as 1 minus sine squared and cube that out. And we'd get a bunch of sine to the sixth stuff. Well, that doesn't seem helpful to me since if I can't do cosine to the sixth, I don't know why I'd think that I'd be able to do sine to the sixth, right? Plus other terms. The other ones that I see over here are this guy, cosine squared. Well, this one again looks like it's in a sense just going to swap out cosine squared terms for sine squared terms, plus some other cosine 2 theta terms. That immediately gets a little bit, I'm nervous about this one because now our argument inside of our trig function doesn't even match, a single theta versus 2 theta. And again, if I'm swapping out squared terms for just more trig squared terms, like did I really help myself? So therefore, this one here seems maybe, and again, I'm not saying I know that this is the most helpful. You're going to make a lot of guesses in this chapter. This one maybe seems more helpful for me because what it seems like it's doing is it's taking stuff that's cosine to the second power and rewriting it as cosine to the first power. It seems like this at least could help me out with a little bit of like dimensionality reduction, right? It seems like we could end up with just some like cosine cubes over here. And I guess it's not clear to me how that's helpful, but I'm thinking to myself, like at least this does some reduction and just instead of just swapping cosine squareds for sine squareds, which doesn't seem like any sort of reduction at all. So this maybe seems like something I want. So cosine 2 theta equals 2 cosine squared theta minus 1. So let's pop back over and see if that's a help to us here. So I'm thinking that I've identified maybe an identity that I maybe care to use. So we just saw our identity of cosine 2 theta equals 1 plus 2 cosine squared of theta. I kind of want to swap this out the other direction, so I'm actually thinking of this as, and wait a minute, did I just get that wrong? I did. Oh man, I got the wrong. So see, I switched these around in my head right there. I wrote that all sorts wrong. 2 cosine squared theta minus 1. That's what I'm looking for. 2 cosine squared theta minus 1. So I'm going to add 1 to the other side. There's adding 1 to the other side. And I'm going to divide both sides by 2. And so it looks like a different way to rewrite cosine squared using our double angle formula is as 1/2 of cosine 2 theta plus 1. So I'm going to go ahead and again, I don't know that this is what I want to do. I'm just guessing some stuff and seeing where it takes me right now. It's kind of hard to judge right off the bat. So from 0 to pi of, and notice here that this is the same thing as integral from 0 to pi of, I'm going to just write this differently, cosine x to the 6th dx. This is really how I'm picturing it for the sub I'm making over here, for the swap I'm doing over here. And so I'm really thinking of this as cosine squared of x cubed dx. And that's going to allow me to rewrite this now as integral from 0 to pi of, inside of this big old parenthesis right here, I have 1/2 cosine of 2 theta plus 1. And that's what's all getting cubed. So I'm going to now assess my situation. I'm going to say, okay, can I do it now? And the answer is I certainly don't quite know what I'm doing. I should stop switching between thetas and x's. There we go. That's an x right there. Unclear. That's my answer right here. But I do know what I would do if this was a good idea. What I would do if this was a good idea is I would try and expand this cube right here, right? So I'm thinking 1/2 cubed is 1/8. And I've got here, what, like a 1 plus cosine 2x is what we're cubing. So let's go ahead and expand this here. I am thinking to myself of my, I know how to cube things. I know what coefficients they get. That's my that's my row of the Pascal's triangle right there. That tells me my coefficients for binomial expansion. Um, so what I'm seeing here is this. I think we're looking at 1/8 times the integral from 0 to pi of, I'm going to get 1 cubed times 1, which is all just 1. I'm going to get plus 3 copies of 1 squared, which is 1, times cosine of 2x. I'm going to get 3 copies of 1 times cosine squared 2x. I'm increasing the power on one, decreasing the power on the other every time. And finally, I'm going to get 1 copy of cosine cubed 2x. Now, the reason why this is, I guess it's unclear to me if this is a good idea or not, but here's at least the good news that I am seeing. We have now managed to rewrite something that was originally just a product, right, a power, as something that is now a sum of 4 different parts. And I know that integrals can be broken down over addition, right? So what I see here is not one integral, but 4 separate integrals that all could be handled separately. The extra good news is that I can do the first one easy. I can do the second one pretty easy. I'm going to have to stop and think about this third one here, maybe. But I think I have an idea for the third one, considering we just figured out a way to rewrite cosine squared a little bit easier up here. So I'm thinking that this swap might help us again for the third one. And for the fourth one, what I'm seeing is we have an odd power on a trig function. And when I see odd powers on trig functions, that makes me think about this stuff that we just did back here. Right? Here's an odd power on a trig function, and it seemed nice for us to break it down like this. And actually notice that if you just ignore all of the sixth powers this whole way down, we still could have done this problem the same way, with just that cosine cubed. So it looks to me like I can maybe actually handle all 4 of these parts individually. So let's go ahead and give this a shot here. So I'm going to break this up into my 4 different integrals. 1/8 integral from 0 to pi of 1 dx plus, so I'm going to do some constant coefficients here. This is a constant multiple of 3, and notice that this 1/8 is multiplying the whole thing, so this is now like a 3/8. I can directly do this one. This technically requires a u sub, but I can do that u sub in my head there. For the next one, we're again going to get 3 copies of 1/8. The cosine squared of x, but I think I know how to do this because my half angle formula will reduce that for me. And then on the end, my cosine cubed, which we have only a 1/8 copy of from 0 to pi, I think I can handle this one because I have kind of set myself up for the parts for that before. So here's kind of what I want to do. I'm going to give myself some space here because I'm going to have to show some work for some of these, but sort of not for the others here. So this to me is going to be a 1/8 x, where x is going from 0 to pi. And so it looks to me like this is just going to be pi eighths for this one term that's right there. That's my first term. Hey, we're 1/4 of the way done. For my next term here, I could do a u sub for myself. I think that's a little bit overkill right here. I'm just going to say that this is 3/8. I know that my antiderivative for cosine is going to be a negative sine of 2x. But I know if I took the derivative of sine of 2x, I'd get back cosine of 2x times 2. And I don't want a times 2, I only want one of it. So I'm going to account for that with a 1/2 right there. That's the appropriate constant multiple to cancel with the 2 that would be popped out by the chain rule if we took a derivative right there. This is getting evaluated from x equals 0 to x equals pi. And again, if you don't like the quick thing I just did right there, just do a little u sub. Make u equal to 2x, and you'll get an easy u sub that'll get you this exact same result right here. So it looks like here we're getting minus 3/16 of sine 2x evaluated from x equals 0 to x equals pi. And if I plug in pi here, sine of 2 pi is 0, and sine of 0 is 0. So it actually looks like our total contribution from this piece is just 0. The way that I kind of knew that before was that this graph right here looks like this from 0 to pi. Right? If you can see that picture. And this positive area in the top lobe is exactly equal to the negative area in the bottom lobe right here. And that means that all the area canceled out when we integrated this guy right here. So we get a 0 component from this one. So pi eighths is our contribution from the first guy. 0 is our contribution from the second guy right here. So now let's move on to the third one. And now for this guy, we're getting a plus 3/8. But I'm thinking to myself, this might actually be better now. I know a way to rewrite this not as a squared cosine term. And again, I don't know what the antiderivative of cosine squared is, but I did learn a moment ago that I can rewrite cosine squared as 1/2 of cosine 2 theta plus 1. All right. Oh, I'm running out of room for the good one that's over here, though. All right, I'm trying to get it all mashed in here. All right, so this is going to be 3/16. I'm extracting the 1/2 times the integral of cosine from 0 to pi of cosine of 2x plus the, I'm going to put, here's what I'm going to do. I know that I've got an addition in there, so I'm going to rip this apart into the two parts here. Here's my dx. And I've also got the integral from 0 to pi of 1 dx. And so here's what I know. I already did this one a second ago. I did this cosine of 2x 1 second ago, this integral, and I got 0. So I'm good with this one already. So this should be plus 3/16 of 0 plus, I've also already done the integral from 0 to pi of x, and I got pi. I just kept 1/8 of it, right? So that's going to be pi. So it looks like this is going to give us a 3 pi 16ths contribution. So all we need to do is work out the last one, and we are good to go. We just need to do this guy right here. So let me just do this. I'm going to just call it last one in a box right there. And let's just come down here and do last one. That was the integral from 0 to pi of cosine cubed of x dx. Now, again, my lesson that I learned in our second example is that odd powers of trig functions often are best dealt with by extracting one of them and rewriting the other grouping in terms of its partner trig function. So I'm thinking to myself that I might want to do something like this. The reason why I want to do this is because now I can rewrite cosine squared as 1 minus sine squared. And the good news is again, now if I make my choice for a u substitution to be u is sine, then du will be cos x dx, and I've got that part. So I've set myself up for a good u sub here. So u equals sine x, du equals cos x dx. And it looks like we can do 0 to pi, 1 minus u squared, and cos x dx is just du. My integral here, integral of 1 is going to give me u. Oh my gosh, I want to make sure I don't do this wrong. These are x values now. I've converted into u, so I should remind myself that those aren't u's, those are x's. So I'm going to get u minus 1/3 u cubed evaluated from x equals 0 to x equals pi. And so all we got to do is go grab our u was sine. So sine x minus 1/3 sine cubed x evaluated from x equals 0 to x equals pi. And what I see we're getting here is just, well, when I plug in pi into each of these, sine of pi is 0. And sine of 0 is 0. So it looks like that was all actually a whole bunch of nothing right there. Does that make sense? Wait a minute. Am I right? Sine is an odd function, right? Because there's our, wait a minute, from 0 to, why am I talking myself out of this one right here? Sine cube, sine of pi is 0, right? Yeah, well, I guess this is a, right? Is that my contribution? This guy right here? So all we're getting then is a plus 0. This would be 5 pi 16ths then? Is that what I'm seeing right here? So we end up getting for our 4 parts, all right, let me just copy these guys. Pi eighths, 0, 3 pi 16ths, and 0. Yeah, I think that's the answer I remember seeing for this guy right here. And again, and I guess what I want to point out here is I kind of feel like sometimes I'm like, oh yeah, duh, I probably could have figured out that that was going to be 0 beforehand because it's probably something geometric I could have seen. But realize that the only reason that this went to 0 is because we actually evaluated this over some specific bounds. If this was a general antiderivative that we were hunting for, then we would have, kind of needed these parts of sine minus 1/3 sine cubed right there for that guy. So again, let's kind of like talk back through what happened in this one, kind of see the lesson that's associated with it here. This one was a bit of a booger right here, right? But again, when I saw that cosine of the 6, the thing I said to myself was, good, that's an even power on cosine. I should think about cosine squareds. So the first thing I did is I got in terms of cosine squared. But what we've kind of been doing, one of our moves with cosine squared, is to just rewrite cosine squared as 1 minus sine squared. But if the only thing we have is cosine squared, that's not a helpful move because now we just shifted around our problem to be about sines instead of about cosines. It didn't help us solve anything. On the other hand, when we did get this sort of reduction in dimension here, when we went from a squared term to a non-squared term, that actually opened up some new choices for us here. So I used my trig identity to rewrite cosine squared as 1/2 cosine 2x plus 1. I cubed out the whole thing. You could FOIL this if you want. I kind of used some helpful information from my Pascal's triangle here about what constant coefficients I knew I needed to multiply into each of these guys. Notice also, by the way, this 1/2 was covering all of this. So the 1/2 was getting cubed, but 1/2 is also a constant multiple, which is why it was allowed to be pulled out front here. Integrating my way through each of these 4 parts. I know there's a lot of work on this page here, but I've sort of got my 3 columns of work here. And then I ran out of work room for the 4th column of work here to get to the end. But there's really 4 different things that happened here, right? This was a direct integral. This was u sub I did in my head. This was me reusing each of the 2 previous, reusing our trig substitution and then reusing our 2 previous results from the same problem. And then the last one here was reusing our technique that we used in the previous example, which is if you've got an odd power, it's often good for you to pick off the odd power and leave yourself with groupings of even powers, rewrite the even groupings in terms of their opposites trig expression, and then apply u sub, since the partners in our trig expressions are often also the partners in our derivatives. Those end up being together often, and it helps us quite often to actually perform the integration in here. And just finally, remember every time, I know I've yelled at you a bunch about it before, but anytime you're doing definite integrals, be smart about your labelings here. Don't go hopping back into U land with your X expressions or something like that. Make sure you convert all the way back before you wrap it up here. And then this is just my bookkeeping. Here's the 4 parts that I got out of expanding that cubic and the 4 contributions that they made. Common denominator, 5 pi 16ths, I think is what we're hunting there for that final answer there. All right. So this is a super cool problem because we just used like 6 different techniques there, all coming together in one place. And so I do want to do actually 2 more problems here. I think this one will maybe be like the most work for writing, but the other 2 are also very interesting and kind of hopefully you're getting this feeling that a lot of this chapter is about kind of, again, getting some intuition for things that man, do I hate calling anything math in math a trick. But it's like if you didn't do this appropriate trig sub, you would never be able to see how to perform this integration. It matters that you do some non-obvious algebra and trig steps often first. And so it matters that you're comfortable just trying some stuff. Just write some things down. You don't have to be right because you're writing something. Write down every single trig identity that you might use for this and do the algebra on all of them. And then stop and say to yourself, okay, which integration do I think is going to be most reasonable? And if none of them look good, then keep trying new swaps. This was still not obvious to me that this was a good idea at this step. It still wasn't obvious to me that it was a good idea at this step. It felt a little bit better to me at this step right here, but honestly, I got nervous again thinking about this cosine squared and this cosine cubed. But when I realized that cosine squared gets the exact same swap as we'd already done once before, and once I realized that cosine cubed used the exact same technique as we used in the previous example right here, that kind of made me be like, okay, maybe this is actually the way to go. So I want to continue to emphasize to you guys that like, I really wasn't sure that any of this work was a good idea until I spent some time looking at the fourth line of work. This is where I started to believe that anything I'd done was useful. And so I want, again, to emphasize to you guys, like, nobody just looks at these and is like, oh, I'll tell you what to do for this one. This is, in a big, big way, this is like, start trying some things. And you need to either talk yourself into it or talk yourself out of it once you've kind of seen some alternate perspectives from which to view these problems. Once I talked myself into each of these individual parts, all the rest of this gnarly looking stuff was just me doing the doing. The hard part for me was really getting to this line and convincing myself that this line was useful. That wasn't obvious, and I had to do some work and thinking to get there. The rest of this was just doing the stuff that I convinced myself I was going to be able to do. And it just looks sloppy because I'm writing in this marker style pen right here. That's all. So I think you guys can do this one. It's more about seeing the trig subs than it is about being good at calculus for a lot of these problems right here. So let's see some other examples of some things that could crop up. And again, I hope the lessons that you're kind of remembering for all these things, that you're realizing that all of these are trig lessons that we're kind of realizing here, and not necessarily so much calculus lessons, aside from the calculus lesson of you want to build a part and its derivative if you want to use u sub. So let's look at this guy as our next example here. This is going to remind you a different thing that I know that a good chunk of us have forgotten with respect to trigonometry here. So let's go ahead and rack our brains as to thinking about what could we possibly be doing in this setting right here. So here's the thing I like about this, and here's the thing I don't like about this. We've got a cosine term and a denominator down there. And the real bummer is that it's got a -1 attached to it. So what that says to me is I can't just deal with that cosine x. It has to be all of like cosine x -1 has to be a term that I collectively deal with right there. Cosine x -1 feels to me like it's almost like a substitution that I want to make. It's almost a sub of interest to me. But like, I don't see really, I guess this is actually sort of like a cosine -1, but I certainly don't have like a square root of it here or anything like that. I don't know. That square root makes me nervous. I guess technically that's an option that you should sort of consider there, but that these look a little bit gnarly to me for what I'm considering. Really, like the thing that I'm seeing is like, I want this to be just the trig identity, but really here we need to have a cosine squared, right? We don't really have that. We have like a cosine -1, not like a cosine squared -1. And so that's like kind of close, but like, I don't know, like here's sort of a cosine squared -1, but it's actually 2 cosine squared -1. Honestly, this one doesn't look too bad right here, but doing addition and subtraction in the denominator is going to be kind of a bummer. So the thing that I guess that I feel, like this is my like trig spirit, what my trig spirit is telling me right here is, I feel like this problem would just be a lot cooler if we had that cosine being squared. Like, I often like to think to myself, this is one of those like dumb student things that's actually practical in the real world for myself. My dumb student thing that I do is I say to myself, well, if I were allowed to just rewrite this problem to be a problem that I think would be slightly easier, how would I go about doing that rewriting? And I think that the thing that I kind of want here is to see that cosine term being squared, because a cosine squared or a sine squared with like a plus or a minus one, that's always stuff we can like swap out for the other, right? And I can honestly say I don't even see what calculus I would do after the fact. Just my trig spirit is telling me plus or minus one. I want to see a squared trig term that's with that, right? So the question that I would ask to you guys is, what trigonometric or algebraic beating stick do you own that can help me just sort of make that squared? So here's what I'm going to do to make that happen. What I'm going to see here is I want to get my window back up. I am going to hit this thing with what we call the conjugate. And what we want to remember here is that conjugates are, if I have a plus b currently or a minus b, I can always switch the sign and multiply by otherwise the same grouping, and that's going to give me the squared versions of each of the two terms that I've got. That's kind of my plan with conjugates here. So what I'm going to do trigonometrically here for myself to see if I can rewrite this guy a little bit different is to do a cosine of x minus 1. There's my original. And what I'm going to multiply in here is a cos x plus 1 over cos x plus 1. I'm going to multiply by the conjugate of the denominator. And the reason I'm thinking that that's going to be helpful to me is because now I'm going to end up with some sort of cosine squared stuff in the denominator. And that's stuff that I can play around with to turn into like a sine squared or something like that. So in the numerator now, we just have cosine of x plus 1. In the denominator, we have cosine squared of x minus 1. And that is awfully close to something I know as a trig identity. Sine squared plus cosine squared equals 1. And so it looks like cosine minus 1, cosine squared minus 1 is negative sine squared of x. And by the way, be a little careful here with these. This is a really easy mistake to make because whenever I see cosines and like a minus or something like that, I'm always like, ha, nailed it. Turns out cosine squared x minus 1 is actually negative sine squared. I actually made a mistake when I was doing mine earlier. I dropped this negative and got my answer wrong here. So just be a little bit careful with your identities right here. So what do we got? If I were, and again, I'm going to continue to be honest with you, and I'm going to say I'm not actually sure that this is helpful yet. I'm just doing stuff right now, hoping that eventually I'm like, oh, hey, look, it looks like we can do this one. So what do I see? Cosine of x plus 1 is just our numerator. In the denominator, we now have a negative sine squared of x dx. The reason why this is starting to look promising to me is because I could make some choice like u equals sine of x. Then I would be getting something like du equals cos x dx, and I sort of have that here. But this plus 1 now is now my current least favorite part of this problem. Because that minus 1 was there, that led me to want a squared on the cosine, which I forced to happen. I got my beating stick out. But to bring in this squared onto the cosine, that required me to bring in a cosine x plus 1 up in the numerator, and now the plus 1 is what's bothering me right here. Otherwise, I think I could do these two terms together. Turns out this is an easy fix right here. And I want to say to you guys, like, what I know happens to every student is that you just see, like, this is the page that you all get worried about right here. I know it because this looks hard and weird and difficult, right? But this is not so much because if you can just do integration, now I'm just saying do this integral. There's 4 of them. That's not really that bad. The other thing is that I know that you guys have started training yourselves to look for U-subs, to look for integration by partses. What I know is the case is that a lot of you guys have stopped already remembering to just do super basic algebraic things, such as break this apart into 2 integrals. That plus 1 is the thing that's bothering me more than anything there. So separate it out into its own issue. Right? The whole beauty of having addition in the numerator and not having addition or subtraction in the denominator is we can just rip that apart. It's the 2 different fractions. This is just cosine over sine squared plus 1 over sine squared with that negative attached to that thing right there. And in fact, gosh, what I should be doing here is well, never mind. I'm going to write this now just as, so now here's my new move. I'm going to write this as the negative of cosec integral of cosec over sine squared of x dx plus the integral of cosecant squared of x dx. Right? So those both had a negative on it. I just factored that negative out so we don't have to think about it here. So what are we going to do? We got two integrals to do. Let's see if we can do them. The first one here, the reason why I like this is because this feels to me like that u sub that we're thinking that we want to make. U is going to be sine of x. Du, therefore, is going to be cosec dx. And I've got a cosec dx here, and I've got u stuff on the bottom. So I'm going to get the negative integral of 1 over u squared du. So that's my first one. I can do that. I know I'm good with that one. So let's go ahead and see what our second part looks like. For the second one, we need to undo this one. I guess I wrote that as cosecant squared. And by the way, you guys should all take that as, oh wait, sorry. Oh no, sure. Oh, I see what I did. This is my mistake. That was a squared right there. We got that same denominator right there. So that is a cosecant squared right there. And again, this is just like me claiming, I think, that some of you guys probably forget things, like just rip stuff like that, fractions like these with addition to the numerator and two different things. I'm also thinking that some of us are forgetting which ones of these we can just straight up do. So I'm going to scroll back up here for you real quick. And it looks like this is actually something we know the antiderivative of. Cosecant squared is the derivative of cotangent. Therefore, cotangent is the antiderivative of cosecant squared, give or take a negative. I factored out the negative, so ours is positive. So it looks like that integral expression that we're looking for is just going to give us negative cotangent of x. And that's all. That is, I'm just pulling this directly from the derivative that we already know. Since the derivative of cotangent is cosecant squared, the integral of cosecant squared is cotangent. And I just didn't say some negatives in there, but those are easy for us to pick up. So it looks like we basically have this one now. It looks like this guy right here is literally just negative cotangent of x. And I'll stick my plus c on here since I'm a responsible mathematician. And all we got to do is wrap up that u sub and we're good. So I'm getting negative. This is really like, this is better for me to think of this as u to the negative 2. That's always smarter as a power. Negative 2, I'm going to add 1 to the power to get negative 1. And that negative 1 is going to come down as 1 over negative 1 is the coefficient. So I'm thinking negative of negative 1 over u. Looks like we get a minus cotangent of x plus c. And so this is going to give me u was sine. 1 over sine is cosecant. All I got to do left is distribute this negative onto each of these terms. Notice, by the way, I'm not writing it as a minus c because if we were given the extra information to solve for c, it wouldn't matter if that was a plus or a minus. That negative in a sense will fall out when we do the computation right there to be accounted for. So it's typically the case that even if you're going to do things like a multiply your c by 2, you can pretty much just call 2c c again because we'll end up solving for any c is a constant multiple. Any constant multiples being multiplied by in a sense can get absorbed into the idea of what c is. We would all still end up solving for the same correct value if we were given any initial conditions right there to solve for that guy. So this one, the big reminder here for you in this one is that we actually kind of really like squared trig terms almost more than we like not squared trig terms. So conjugates are always our good way of making stuff that's not squared be squared so that we can do a lot of our trig identity swaps. So this is just one of those things, if you feel like, if you're sitting there and you're whining to yourself with your book open and you're saying, man, I could do this problem if that thing was squared, that's not just a whine. That's a good thought. That means to you, maybe I should use a conjugate to actually get that stuff squared. That's our good strategy for that one. So conjugates can make non-squared terms have their squared components instead, right there. And then we just made some swaps. I wasn't sure that I was going to be able to do this one until we got to about here. Here is where I talked myself into this one. So again, this was me doing a lot of doing without being sure that it was right until I got to here, and then I kind of talked myself into the fact that I'd be able to do the calculus from there, and I was. So let's do one more problem here. Today is maybe a little bit long, but that's kind of the way I think some of these are going to go here. I think I'm kind of on pace for what I was sort of expecting here. This one is, and by the way, I'm also going to tell you right now, this is just straight up example 8 from the book. This is just such an awesome example that I can't not do it. So this isn't even like a homework problem. Like they literally do this one in the book. Part of the reason I want to do this one right now is because if you are a little stuck maybe on one of your homework problems, the take home, the by hand homework from last week, this is actually going to have one of our key ideas for one of the by hand homework from last week for integration by parts. So maybe this will, if you've been maybe stuck on that part, maybe this will be helpful for you to see this here. So, secant cubed. Boy, what a bummer. My big bummer here is that, like, I know that if I had squared trig terms, then, or even powers on trig terms, then my lesson to myself is, well, good, we like even powers. Let's rewrite it as powers of even powers and use our double angle identities to reduce them in power and order and magnitude. My other thing so the thing I don't like here is this is an odd one. So that seems to me to feel like we're going to want to like pick one of the terms off to get an even grouping. But the problem here is that I don't have like secant stuff and tangent stuff or something like that. Like when we had previously seen a problem that had these odd powers, it was sine powers and cosine powers, and that was good because we wanted to like rewrite one in terms of the other using their u subs, right? One as the derivative of the other, stuff like that. So I'm just saying it's super not clear to me exactly what to do right here. So I'm going to start making some sort of guesses, right? My first statement is obviously I don't know a direct antiderivative for this. I'm thinking we have to do some sort of identity, a u sub, an integration by parts to make this happen. So I guess my first move is let's go over and just look at our identities. And I'm going to say to myself, do I see anything that looks friendly with secant cubed? One thing that's probably worth noting here is I do see that we do have a secant squared identity right there. One of our Pythagorean identities, it looks like secant squared is 1 plus tangent squared. So I'm going to store that one away in the old memory banks right there. Not directly obvious to me how I want to use that, but maybe that'll come up. What else do we got right here? I'm noticing over here I see no secants. Our half and double formulas are pretty typically always only written in terms of sines and cosines. Product of sum, sines and cosines, sum of the product, sines and cosines, sum and difference, sines, cosines, tangents. This is actually the only secant I see out here that seems like it might be something of use to me. In a sense, that's good because I don't really have other options. In a sense, that's bad because I don't really see directly how this option is going to help me. So let's see if I can use this idea right here to help me out. So here we are. So the one thing I know I can rewrite secant as is as, or sorry, I can rewrite secant squared as is as 1 plus tangent squared. So I've got secant squared equals 1 plus tangent squared. So what that is going to suggest to me that I maybe want to do is something like secant squared of x times secant of x times dx, right? This is me just breaking up the cube into a 2 and a 1 right there. Again, I'm shooting blind right here. I'm hoping something's just gonna pop up and slap me in the face, and it hasn't happened yet. So I don't know. What's my next move? Maybe we rewrite secant squared as 1 plus tangent squared. This seems kind of promising to me because what I know is that these two things have a derivative that's related. My immediate trig calculus instincts say, oh yeah, the words tangent, secant, and squared belong together. Let's go see how. I am not misremembering. The derivative of tangent is secant squared. Does that help me then? The derivative of tangent is secant squared. So can I do something like u equals tan x? Then du is going to be, the derivative of tangent is secant squared x dx. Now, This looks super close to what we want, but it's kind of off, right? The thing that you should be seeing is we don't just have we don't have secant squared dx. We only have one secant times dx right there, not two of them like we need to make this swap out for du. So this seems tantalizingly close to being a useful u sub right here. But basically my issue is that I feel like sort of like my squared is in the wrong place, right? Like if I could pick u to be tangent and tangent was standalone and the secant was what was squared, this would be a good u sub. This would only work if squared was on the other term right there. We're just not quite getting the parts that we want right here. So I'm just going to say this right here. Not quite. It doesn't look like this is panning out for me to do the thing that I want it to do. And it's close, right? I'm seeing that there's sort of some parts. I'm definitely recognizing that the derivative of secant or tangent being secant squared is maybe something that's going to crop up to be relevant here, but I don't quite see it. So here's what I'm thinking to myself. I still believe that ripping apart a cube into a squared and a single is still generally good for me. I don't feel like this was a good move for me because this didn't introduce for me something that worked for u sub. And also, by the way, I think it's irresponsible for me to move away from this attempt without looking at integration by parts. What could we pick here for u and dv if we we're going to do this? Well, remember that whatever we pick for dv, we need to be able to integrate it to get back. So here's my issue. I could pick, I guess, either of our parts, 1 plus tan x, or tan squared, or secant to be u, because I am capable of taking the derivatives of both of those things. However, the choice that I make for dv, I need to be able to integrate. And I don't currently know an integration for secant, although I should just stop right now and tell you the integral for secant, the book does, and we are going to depend on it for this problem right here. But this is like one of the hardest ones that the textbook does for the whole section. The integral of secant depends, they do this most ridiculous conjugate method to get at it that I would never expect any of us to come up with on our own. So it is actually true that selecting this guy right here for dv is technically something we could use, since in a sense you are allowed to simply quote what the integral of just secant is. The book does give it for you here. But if I choose 1 plus tan squared to be u, then you should see that the derivative of tangent squared is going to be what, like 2 secant to the fourth of x? And I'm not quite sure that increasing the powers into a secant to the fourth for du is what's going to be helpful to us, right? The derivative of tangent is secant squared. So if we have a squared tangent, we should end up with like secant to the fourth stuff in there or something like that. It doesn't seem like, it seems like we're building again and not like decaying like we want to happen with integration by parts. So it's true that I am lamely attempting this integration by parts and suggesting I don't think it's going to work for us, but that's kind of the case right there. Like making that choice for u and dv is going to not quite be awesome for us right here. So how else could I maybe do this? All right, so I'm going to attempt start over right here. I still am starting with the same thing. We're still doing secant cube. Oh my gosh, I can't write. But I'm going to make a slightly different maneuver here. The one thing we really haven't done here is we haven't gone just straight into trying an integration by parts yet, right? We keep on trying to do more stuff than this first. Is there some smart pick that I could make for u and dv that's going to make this work out here? Now remember, whatever we pick for dv, I need to be able to do the integral of. I need to know an antiderivative for. So my question is, of these parts, which of these two things do we know an antiderivative for? Well, I actually do know the antiderivative for secant squared, because the derivative of tangent is secant squared. This seems to me like to be a pretty good choice for dv, because I can directly integrate that and just get tan x. That's doable for me. I know that one. Also, u then would be secant. And although this is one of those slightly annoying ones that we probably need to go look up, I remember that the derivative of secant is going to be secant tangent. So the derivative of secant, if we have u being secant, the derivative of that du is going to be secant tangent. And we get the dx parts that go with it there, right? So this can be a u sub. So I'm going to again say the same lesson from all day today. It is not clear to me that we're doing any good math right now. I'm just trying stuff. I'm flopping some stuff out there, and I'm hoping something's going to slap me in the face when I see it. Right? I want to continue to remind you that the integral of secant is not something that you currently know, but technically the book is expecting that you are just going to reference it since they did it immediately before they do this example, and it is never something I would expect you to be able to come up with on your own. So I'm telling you, even though I know that you don't know the integral of secant x dx, I'm telling you it is a viable lookup one. And so we will assume that to be something we know for the sake of doing this problem here. So let's see what this is going to look like here. We've got, this is our integral of u dv, and so we want to say that this is equal to u v minus sv du. And to us, that's going to be u v, so secant tangent, minus the integral of v du. v du. All right, it looks like we've got tangent times secant times tangent times dx. So in total, it looks like v du actually has a secant tangent squared dx. And again, I'm going to keep saying the same thing over and over and over. It is not clear to me that this is even a good move. This is anything I can even handle. I'm just trying stuff until I get to a brick wall. And I'm not at a brick wall yet. I'm maybe a little confused, but I'm still wandering. I'm still going somewhere. So what do we got? So we're done with this part. Now we've replaced this integral that we can't do with this integral that we can maybe do. I don't really know. So do you see anything in here that looks like this is maybe doable? Well, I clearly have two components of this integral, a secant and a tangent squared. And what I always like to ask myself when I see two components is, u sub is easiest, integration by parts is second easiest. So I'm first going to ask myself for u sub, do I see in here a component and its derivative? And hopefully you're watching me just circle those parts with my mouse. The answer is yes. This is a pretty direct u sub right here. U subs never seem obvious in trig land because we have to like really remember our trig derivatives and integrals. But once you see this one, this is like as direct as a u sub actually gets. I'm going to be responsible here and do like an m sub since I've already used the letters u up here. So I'm going to select m to be secant of x, and then dm, the derivative of secant is, or wait a minute, am I doing this backwards? Wait a minute, didn't I? Wait, the derivative of tangent is secant squared, right? So am I, what am I? Oh, so it feels to me now like I am still running up against my same issue right here, right? If I tried to pick this to be C, and again, this is kind of the wrong sub that I want to make right there. If I picked M to be tangent, then dm is secant squared x dx. And again, that squared right there keeps screwing me up. I feel like we're back in my same little bummer situation as where we were before, where I want this squared to be on the other part, but it's just not. But I think we're in a slightly better situation than we were before. Here's the thing I'm realizing. So I'm still working on this being the hopeful thing that's going to take me home on this problem. I don't want to forget that we identified a pretty useful substitution up here. Right? This is my way to rewrite tangent stuff, tangent squared stuff, in terms of secant squared stuff right here, right? Notice that this substitution was useless to us the first time we tried it here, but maybe now this is actually going to be more useful to us. I didn't want to use that swap right here because it would have prevented me from setting up my integration by parts. But now that I've set up my integration by parts, maybe it's helpful for me to swap out tangent squared of x for, so tan squared x should be secant squared minus 1, as it looks like the swap I could allegedly make here. So let's see where we're at. So I'm going to go ahead and indicate that my u sub, nope, that didn't work right there. But I don't think we're totally screwed yet. I think we could still maybe make this guy happen. So I'm gonna try and be clean with my work here. So I'm gonna come back and kind of rephrase where we're at. We're currently trying to evaluate secant cubed of x dx. How we've currently got it written is as secant tangent. I'm just rewriting this guy right here. Secant tangent minus the integral of secant tangent squared. But now I'm thinking my sort of last ditch idea here is tan squared is, and I'm forgetting it already, tangent squared is secant squared minus 1, it looks like. So I think I can rewrite secant cubed x dx as secant x tangent x minus secant x times secant x squared, I better write my squared in the correct spot right there. Dx. So I'm going to go ahead and say this for the bajillionth time. I literally still don't know if what I'm doing is going in the right direction. I'm just trying stuff until I literally don't have anything else left to try. Where are we at? Well, I'm thinking to myself, I want to distribute this and rewrite this as two integrals. So what I'm seeing here is that this is really, well, crap, this is secant cubed x dx. It looks like we've gone in a completely full circle here. So that makes me nervous. Plus, distribute the secant. Notice there's a negative here and a negative here for a positive. We're going to get our secant x dx. So we need to seriously stop and assess if we're just going in stupid, dumb circles right here. And this, to me, is one of the sneakiest good things ever. It's super not obvious that we just landed in a great spot right here. So here's what I want you to recognize. Our efforts to take the integral of secant cubed, we've done a page and a half of work. We've done a u sub that didn't work. We did an integration by parts that didn't work. We did an integration by parts that maybe worked. We tried to do a u sub to follow it up that didn't work. We came back to our integration by parts. We did a trig sub. The trig sub has allowed us to rip apart the new integral from our integration by parts into two different integrals. One of them is the integral that the whole time we've been trying to solve for in the first place, and the other one is this guy. Now, are either of these integrals even good news for us? That's the question, and here's my answer to you. The answer is yes for both. The answer is yes for this last one, because as I've been promising you, this is one of those ones where the book is anticipating that we're just looking up. I'm just going to tell you what this integral is right here. I'm hoping that I made that clear this whole time, that we will assume that just seeing the integral of secant is good news. It's a look-upable integral right here. It turns out that the integral of secant of x is the natural log of secant plus tangent. There we go. We'll have that as a written one. How is this helpful to us at all? Well, notice that what we're really trying to solve for, you should be suspicious as to why am I writing secant cubed over and over and over again for our integral on the left. That's because if I want to solve for what is the integral of secant cubed, I just really actually have two copies of this integral on the left-hand side now, right? Notice that to try and define what the integral of secant cubed is, one of the terms in its definition was itself the integral of secant cubed, but that's fine because I'm just going to do a shuffle here. I'm going to shuffle over this part so we actually have two copies of it. So I'm going to now get 2 integral of secant cubed x dx because I've added over this one copy of it to the other side. Over here we now have secant tangent. I'm telling you that this is given in the book. as the natural log of secant plus tangent. And the book does show you where they get that integral from, and you could do it. You can do the math that they do, but they start by doing something similar to a conjugate like we did back up here. They start by doing something like, oh, let's multiply by a smart fraction to give us something that's easier to work with. But in a conjugate, I would expect you guys to come up with this idea now that you've seen this. They multiply by something that's not quite a conjugate. It's still something like of this structure right here, where it's like a fraction that's equal on top and bottom. But it's one that's just really not obvious as a guess that you would make. It's not a conjugate. It's some other fraction that's itself, that's a number over itself. And it's a weird one that's just like you would have never seen it. But if you see it, you're like, okay, I guess, yeah, you're right. Technically, that's correct. But like, it would take me days to guess at that one if it was the only thing I was doing. So I know it's so the book justifies this, but it's a tougher one, and so I approve of the book just saying, listen, here's the integral of secant right here, and here's how we got it. It's a little bit of a hairy one. So the point is, here's our UV minus this is our SVDU. One of the parts of our SVDU was actually what we're trying to solve for the whole time, so I added it over so we have two copies. The other part was one that was given to us before. So it looks like we're basically done here. I'm just going to divide both sides by 2. And I guess there should probably be a plus c in this whole dang thing. And again, I'm going to say about these constant multiples, whether this plus c is inside of these parentheses or not is only affecting if we're going to have c or like half of c. And to me, those are the same thing. Half of c might as well be c because it absorbs all constant multiples. So whether you would write this c inside the parentheses or outside is completely irrelevant. If I were to say to you, and you are given the initial condition that blah, blah, blah is blah, 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 then you could solve for C, we would all still get the same C out there or the same equivalent expression at the end. So I do want to give this name of what happens here. Whenever you're attempting to perform integration and some integration by parts leads you to just doing more of that same integral again, that's not a problem. You're just accumulating more copies of the thing that you are interested in solving for. The name for this is called dump truck integration. I guess because it's really like you're filling up a truck with an entire load of the thing that you want. I don't know, whatever. I like the name of dump truck integration, but dump truck integration is where you perform a series of calculus steps. It seems to have taken you in a circle back to where you started, but that's actually useful because then you can just move this unknown term. It's just one of the unknown terms. You can just continue to solve for the unknown term, and it matters that you write this term over here on the left so that you can accumulate 2 of them. Notice that if I literally just wrote my equal sign the whole way down, I would have gotten to here and I would have been like, what the hell, man? I don't know what to do with this one. The fact that I was reminding myself what we were exactly computing the whole time helped me to say, oh yeah, just add this over and now we've got 2 of them, and so divide by 2 to solve for what this integral is going to be right here. So kind of hairy example right here, but individually I expect that all these things are things we can do, and realize that, like, I don't know, I mean, I did these before lecture today to make sure I wasn't going to look like a fool when I did these, but like, this was natural. All of this happened. If you want to see my notes, I made every one of these mistakes organically along the way. I kept trying to do these things. I kept making guesses. Some of them worked, some of them didn't. Don't get discouraged. A big, big lesson about this section is you need to have the mathematical fortitude to push on through even if it's not clear where you're headed, and to constantly be saying to yourself, is this looking better for me or not? And to not get worried if the answer is no, but to help yourself recognize when the answer is yes, so you can be like, cool, I think I found the thing that I'm hunting for here. So I'm going to kind of wrap this up by saying one of the things I didn't do here today is I did not just directly discuss the 2 very good boxes in our section that say strategies for integrating sines and cosines with odds and even powers. What should you do? Integrating just sine or cosine with an odd and even power. What should you do? Integrating tangents and secants with odds and even powers. What should you do? And they kind of give you like a general strategy for all these things. I love that they're not giving formulaic things because we are beyond that by now. Like, You need to be a good thinker and you need to just be okay with trig. I don't care if you remember one single identity from trig class. I do care that you have access to this PDF for every single integral that you ever do that involves trig in it for the rest of the semester and for the rest of any calculus or any math class you take for the rest of your life. You should be competent in navigating these identities. Again, I hope that you learned where these came from and why these are true in trig class. That's not what this class is anymore. At this point, I care that you can just use these, manipulate them meaningfully here to actually get at the parts that we want to be able to get at here. I'm feeling like by the way, I feel like I kind of did something dumb here. I'm remembering something out of my notes here. I'm going to go back and make a fix to something because I actually did something bad here. Okay, I see why I did that thing wrong. Okay, here's my dumb edit right here. If you're still with me, great. I'm going to make this edit in red because I realized that I'm like remembering a part of a problem that I made a mistake of, and I'm remembering it because right now I'm staring at my identity sheet, realizing that I failed with an identity earlier. So come back up here with me and stick this out for 1 second. I dropped a term back in one of our examples here. It was associated with this. I think all this part is good. Here's the thing I made a mistake on. I know it's very hard to identify my mistake on this page right here. So here's what I'm going to do. Here's what I'm going to do. I am going to circle this right here. And I'm going to say I made a mistake. All right. I made a mistake in that block right there, and I'm going to go fix it at the very end of this document. So if you guys are looking for this in the document later, you can grab that there. The thing that I failed to do here is that was a cosine squared of 2x. 2x, not 1x right there. In fact, I even did it right there as well. So I'm going to go fix that right now. What we should have been computing right there, we had we were trying to do the integral from 0 to pi. We had 3/8 of the integral of cosine squared of 2x dx, not 1x. That was my error that I made in doing that guy right there. I'm glad I wrote this out so I could kind of see that and remember that I did that right there. So it is still the case that I want to use our double angle identity here of cosine squared of x equals 1/2 1 plus cosine 2x. But you should notice in this case here, we have a cosine squared of 2x. So this should then become a 4x, double that. Whoops, now we're not doing that part anymore. This should now be the, oh, come on, don't press control. 1/2 of 1 plus cosine of 4x here. And the reason it's 4x, and that 4 is like the thing I remembered that I was like, why didn't I ever write that 4 I remembered was part of this thing? Oh, come on with the zoom in. Come on. Every time at the end, I'm like doing good, and then it starts doing crazy things to me. Oh man. Oh man. Now we're zoomed at 240%. We've scrolled away. We've moved things away from where we want them to be. I don't know where my math is anymore. Just let me write right here, word. So again, I'm using my double angle formula here. We didn't have cosine squared of a single x. don't think of this as x, think of this as the argument inside of cosine and then double the argument inside of cosine. Our argument inside of cosine was 2x, double 2x is 4x, and that's why we should actually have a 4x for that guy here. So I think that this should actually pan out to be 3/16 times the integral from 0 to pi of 1 plus integral from 0 to pi of cosine of 4x dx. And we can wrap this up then as, that's 3/16. That is times pi. We already did that one right there. The integral of 1 dx from 0 to pi is just going to give us pi. And over here now, this should be the antiderivative of cosine is sine, but I need a 1/4 sine of 4x right there, evaluated from x equals 0 to x equals pi. I don't think that this is going to actually end up influencing our answer because I'm seeing here that this is still going to be 0. Right? Sine of 4 pi is 0. Sine of 0 is 0. So we're still getting, so So I did make a mistake when I did that. In this case, just because this definite integral went from a bound to a bound where sine was 0 at both, it didn't end up mattering. But hopefully, obviously, you can see that this antiderivative is different than the one that we got originally. If this was a indefinite integral, or if we had different bounds of integration, this difference would have actually cropped up in our answer. It turned out that this component went to 0 in either case right there, but I did technically make a mistake when I did that part in that problem at the beginning. So I guess I'm glad I caught that guy right there. So let me just keep this separated so that when people go to look at the document, they will see that this is where we have stopped and gone back and fixed that mistake right there. And I'm just going to actually identify this, and I'll go ahead and call it a lesson here. So there we go. There's my fix right there. I accidentally did just 1x when I originally did the problem. It should have been 2x. It did result in us getting a 4x inside and a 1/4 outside instead of a 2x inside and a 1/2 outside. It didn't matter in this case because that contribution went to 0, but that was just a particular thing about these bounds of integration. In general, it does matter that I make that distinction. That's right there. Okay, so there we go. I think I've gone on long enough here today. So those are our good trig examples. I hope you guys kind of get the point here that this is very much a section about trig and not necessarily so much about calculus. This is helping you to see that we need to help visualize our u subs and our integration by partses and seeing the parts and asking ourselves, which of these have a derivative that's these other parts out there? Which of these things can we integrate? Which ones can't we integrate? What are the trig identities that I want to use to swap these parts around to make stuff that's actually useful for me? So this is very much a play around with it section. What you're going to see tomorrow when we do 7.3 is that tomorrow is more like actually like doing calculus with trig rather than, I feel like today the trig and the calculus were separate. We would do some trig identity stuff, then we'd go and do the calculus that's associated with it. Tomorrow is sort of like really doing like truly like trig integrals of things to help us identify maybe some areas of things that are better described in trig terms. So this will be a little bit more like convert to polar to help you integrate or something like that. And hopefully it makes sense to you that things like circles have awkward equations in terms of x squareds and y squareds, but have easy equations in terms of like r's and thetas and stuff like that. So tomorrow is more of like trig and calculus are like this, whereas today I feel like trig and calculus were like this. That's my hand analogy for the difference between today and tomorrow. But tomorrow is just, again, more trig with our calculus stuff here. So that's 7.2 and 7.3. So thank you guys for being here today. A little bit of conversation in the chat over there. That was good. And I will see you guys for more trigonometry within our calculus in tomorrow's video.